my pleasure to introduce our next speaker, Dr. Karen Sauer. She's a professor of physics at George Mason. She is, was my faculty mentor and of an immense help to me as I started out here, for which I'll be forever grateful. And she's going to talk to us about some of her recent advancements in quantum sensing and how it can be made, what kind of problems it can be used to solve. So take it away, Karen. Thank you so much.
So in some ways, I'm a little bit the opposite of the talk you just heard. I deal with basic research, so my stuff not go up in airplanes or be buried under sand, or these things are kind of delicate. This phrase, very basic. So you'll see that as I go through it. And I'm going to be talking about how atoms and nuclei can be used, as I just mentioned, in hearing some of this. But basically, if you want a quantum sensor, as he was saying, you want a qubit, you want two-level systems. And really, in order to have a good sensor, you want that the levels to have different populations. You want to have a good population difference. The better the population difference, the better your signal-to-noise ratio is. So if you want to make something that's fabulous, you want to have a good population difference between those two levels. Now, if you want to have a good quantum sensor, I'm like giving you some sort of feedback on what you need. You want lots of whatever your measurement device is. This is this argument like when you go make a measurement, you make n measurements, and then the error goes to the square root of n. So it's kind of standard error bar analysis for taking measurements. So if you're thinking about each atom or each nucleus as a sensor, you want lots of them in order to make a good sensor. So you want to have a good population difference. You want to have a lot of atoms or nuclei. And again, as you've been hearing today, what you want also are long coherence times. You'd like for your signal to stay around for a long time. If you're doing computation, you want it to stay around for a long time so that it can do computation. For the sake of sensing, you want it to stay around for a long time because that tells you how much signal-to-noise ratio you have. It goes in the square root of time. I just do this up here because this is some work done recently by an undergraduate student on zero-field NMR of potassium chloride. This is the potassium part. And this is showing just if you make a signal and it decays. So when I'm talking about a time constant, I'm really talking about I make a signal and I see how long it lasts for. Now, there are tricks that you can use in a lot of these qubit systems that are used, and it's called echoes. So you make a signal and then you can refocus it again and again, and often you can get a big increase in time constant for that. So if you would like, again, the sensitive quantum sensor, you want lots of them. You'd like to have them live for a long time, and you'd like for there to be a large population difference. Or at least you'd like to have 2 out of the 3 if you can't get all 3. So I'll talk to you about 2 systems. So one of the systems that we have that we're using right now in our lab, this is collaboration with Michael Wallace at Princeton. This is actually his cell that these are all built, but we're using it in our lab right now. It's pretty large. It's about 4 centimeters. Again, not small at all. 4 centimeters by 4 centimeters. And what we use the alkali atoms. We use rubidium, and we heat it up. We have to heat it up in order to get a vapor. If you held rubidium in your hand at room temperature, it's just a solid. So you can't use the solid. You have to heat it up. So we heat it up when we get on. Well, we're trying to. I'm pointing to Daniel because Daniel's been doing this work. And Daniel, do we get up to 10 to the 14th per centimeter cube yet? No, but we're working our way towards it. This is a process called curing in which the cells have to sort of over time get up to that level because of surface interactions. So this is an idea of using atoms as a sensor. You have that many. And then, unfortunately, Ritika just had to go to class. Yeah, because these are his crystals, so I wanted to show something from him. So Ritika is another student, a graduate student. And typically think about a solid state device, you've got Avogadro's number per centimeter cube, so 6 times 10 to the 23 centimeters per cube. So like you would think, okay, this one wins in this fight. Which one wins? The solid wins, right? You got to pull out more on one than the other. Well, that's not the end of the story, though. The atoms do have an advantage in that you can take light, you can circularly polarize it, you can give it angular momentum. You can have the angular momentum be absorbed by the atom, and you can get close to 100% polarization. So all of them, remember I talked about that population difference? The population difference is basically everything, all that you can do. So that's fabulous that once you do this, what's called optical pumping, then you can get a great change in polarization, or great polarization, or that great population difference. Now, the system that the Retique's working on, which is a solid state system, okay, yes, it had this really large 6 times 10 to the 23 centimeters per cube. But that thing that creates that splitting, which is actually an intrinsic resonance, we'll talk about that in a little bit, is what's called a thermal equilibrium. So it's polarization by thermal equilibrium. So like you might have learned in your classes that the things end up in the ground state. So, but by how much do they end up in the ground state versus excited state? So that's just this delta E over KT, so whatever that temperature is. And it's not very good, right? So this is 2 times 10 to the 6. Remember the other one was 100% or 1, and this is 2 times 10 to the minus 6. So that's what I was saying about getting the 1 out of 2 if you can. So if you look at these numbers, this 10 to the 14, and this is basically 1, and I've got, let's say, 10 to the 23, 6 times 2 times 10 to the minus 6. So what do I have? Can you tell me, Professor? I can't help it. You end up with the same amount, basically, right? So like you can win in one place, you can win in the other place, or you can win combine them in both. So both of these can be sensitive systems, but for different reasons. Now there's 2 posters that I'm going to try to sell pretty hard right now. So I'm not going to talk about them because they're given as posters. Is there any, oh, I don't know if there's any way to get the top of the screen. Oh well. Okay, so both Retique and Jafar's sitting right there. He's getting a poster, and so is Retique. And they're going to talk about how you can actually use the nuclei as the spy within. The nuclei are there, and inside of these materials are fields, electric fields, magnetic fields, inside the crystal of their own making, just sitting there on the table. And you can use you can measure those fields using those nuclei. Of course, you can also, these nuclei can measure external fields as well. The problem with using them as sensors is because they're actually very sensitive to internal fields also. So they're actually better as a spy within than a measure of external fields. So please go talk to them. I'm not going to steal their thunder, but I'm going to allow them to talk to you. And one of the areas that people are interested in which these fields become quite large, is in unconventional superconductors, in which they get a large magnetic and electric fields in them, and then the nuclei can be used as probes of them. So I won't say any more, but I'll invite you to find those. So I'm going to focus on the atoms for right now. So the first step, as we already indicated with these atoms, is you go ahead and you apply a pump laser, you circularly polarize it, you give that angular momentum. The atoms take that angular momentum and they line up. So I didn't show them lining up, but then they line up with the angular momentum. And that's what we observe. And what's interesting is that, in fact, the atoms, their coherence time depends on how well polarized they are. So you see this blue line over here. This is 0.5 milliseconds, and then this one is 0.06 milliseconds. So the blue line is highly polarized, and the red line is not. And so what's interesting, it's called line narrowing. It's an interesting effect that basically, if you've got atoms with opposite spin, like conservation, they come in and they keep flipping over like this, right? So they take it away. So when they have a strong interaction with each other, and that creates a decoherence time. If, however, they're all polarized, they can't exchange the angular momentum. And so that's what allows the T2 to be much longer. So there's a big benefit to this polarization, not just in terms of signal size, but also in terms of coherence size. By the way, feel free to stop me and ask questions as we go along. So the other thing that I haven't really talked to you too much about is that you put the atoms, you give that angular momentum to them, you give it to the light, and then we give it to the atoms by absorption. And then if we put them in a static field, then we can create the resonance. We can have them be sensitive to a certain frequency. This is a sort of magnetic resonance effect. This is just to give you an idea of what things in my lab look like is that these are green coils. These are green coils, and there's coils around all of them. And we use the coils to determine the frequency. Here you see a set of three. There's two interior ones and one exterior one. And that's so that we can play around. We can have a playground. We can make a field in one and a field in the other, change the other from have two different volumes. But again, you need a field in this setting. So things in my lab, they get hot. And the reason why they mostly get hot is because of this laser. When we turn on this laser, it heats up a lot. It's a 30 watt, which is a lot, pulse laser. And we use it to pulse two cells that are in there, the cells that I was talking to you about. When I went to the manufacturer, this is not off-the-shelf stuff. I have to talk to the manufacturer and then they design it for me. So I don't think anybody else has this in the world. Maybe he sold more. I'm sure he'd be happy to sell you one too. If you want, just let me know and I'll put you in contact with him. But we need a lot of light if we're going to pump a lot of atoms. You see. But I've talked to you about the light being absorbed and the field creating a resonance. So what actually we measure is also light, just like Joseph was saying about his NV diamond sensors using light as the measurement. We're also using light as a measurement. We have linearly polarized light that comes in, linearly polarized light. You can imagine linearly polarized light just means the electric field goes up and down. You can do a superposition of light that goes right and left circuit polarized light. You have to look at the math, and you'll end up being also linearly polarized. So one plus the other equals linearly polarized. And because of the atoms, as it walks through the atoms, because there's some of the magnetization along the probe direction, the index of refraction changes. So I have at least one student in here who's in 306, and we talk about the index of refraction all the time. So the index of refraction is different for right or left circuit polarized light. And so you get a phase shift after you come out, and the light actually polarizes. So we actually measure that polarization of the light is our measurement of our magnetic field. I'm giving you a lot of questions here. So one of the tricks is everybody wants things smaller. Everybody wants to bury things under sand or send them to the moon. And so one of the ideas is there any way to make them smaller, right? Can you instead of having more atoms, can you do something better? And the idea is, yeah, there's a shortcut you can take. And so I'm allowed to say this is a really brilliant idea, because it's not my idea, it's my collaborator's idea. And so he had this idea of taking a really small cell, this is about 1 centimeter in length. What they do is they pass through the beam through the mirror. So right up here you can see there's a pole. They pass through the beam and they pass this back and forth 50 times. It's little itty bitty cells. It's just an amazing thing that they do. So you have 50 times the signal if you pass it back and forth 50 times. And so that's a great winner of signal. So it's a good way to make it more compact. Unfortunately, there's more than one source of noise in these sensors, and you're trying to push it down to the limit. The two big ones, though, are photon shot noise, and that's just the idea that light is quantized. So if you think about light hitting a detector, right, and they're all made of photons, it sounds like rain, right, on a tin roof. So that's noise. That's called photon shot noise, that rain on a tin roof, or the discretization of the light coming in. The other source of quantum noise in the system is what's called spin projection noise. For those of you who have taken quantum mechanics and learned the generalized Heisenberg uncertainty principle, that's this for spin. But more to the point is to say that if you have something that's actually highly polarized in one direction, it still has some, according to quantum mechanics, it still has some area that's around here that you can't get rid of to create noise. So you have these two different effects, photon shot noise and spin projection noise. So when you make it small, you actually win over photon shot noise. Yes. But in fact, do you have any more atoms in here? don't, you have less atoms, right? Oops. Unspent projection noise. So it's kind of all about this balance. So we were like, yes, this is going to be great. It was great, but not as great as we had hoped it was going to be. So we got down with this kind of compact one to about 1 femtotesla times 10 to the minus 2 ferrihertz. So femtosecond 10 to the minus 15 Tesla. Earth's field is 50 microtesla, so small. Small. What's really interesting though is that we've got these noise peaks that are the green and the orange. That's just extraneous noise. And then when we shut off the pumping, you can see the black line, and over to the dot, over to the dotted black line. That's actually spin still making noise. Even though they're not polarized, because of that Heisenberg uncertainty principle, they still make noise. They still see a hump from that. And so we know that this system is dominated by that spin projection noise of the atoms making the noise in their angular momentum. So we said, okay, well, maybe we can have a compromise, me and my collaborators. This is small, 1 centimeters cubed, 50 passes, 1 femtotesla per square hertz. So we try another idea. Okay, well, let's compromise. We'll make it a little bit bigger, 10 centimeters cubed. We'll do 46 passes, so still seeing that. And we're doing now what's called a differential signal. So you might see there's 2 boxes. This is actually fluorescence. So this is the probe light going through the atoms. And because of basic scattering, they're scattering light out to you, and we're looking at them. This is the atoms fluorescing at you, right? It's kind of fun. It's fun to think about the atoms are fluorescing out, and you get to see them. And what we do is we actually take a half wave plate. The half wave plate is right here. You see the little lollipop there? That's a half wave plate. That half wave plate allows us to subtract the optical rotation of one voxel from the other. So it's a very clean optical rotation. And we can get down to 0.19 femtosecond per hertz. That is a world record. That we just achieved, so we're pretty proud about that. We're still trying to figure out how to do things better, though. We're trying to figure out this beautiful device that I was showing you. Either one of this one or that one, they're not easy to build. Right? These multiple passes take a lot of design. And you have to figure out what the input is and what the output is, and these curvatures, and it makes it look simple, but in fact, it requires some engineering really to be able to do this. So we asked the question in a desire to figure out if things could be simpler, is could we just get away with doing fewer passes but more power? Because it's easier to build. I have to go 1, 2, 3, 4. Oh, I can do that. That's pretty simple. You can imagine going into a lab and choosing some mirrors and going like that back and forth. That's not too hard. Or do you stick with what we've done before, which is the 46 passes, but a lot less power? It's a sort of a compromise there. So Barbara Cooper, who just graduated, is doing atomic clocks at the Naval Research Labs. It's kind of very, as we were saying, a lot of these things are kind of interrelated. You think you're doing one thing, magnetometers, and all of a sudden you're doing atomic clocks. A lot of them are just related to one another. So there's this trade-off in terms of the noise between passes and power. So we were looking for that, and ideally these should be the same. Unfortunately, we found that they were not the same, and that there was something that basically happens here that's non-ideal that we need to explore and understand better. So in other words, for now, we need to stick with the more complicated design of more passes but low power. So this is just saying, again, this is the one that won the 46 passes and the 1 milliwatt. And if we take a look at it with the light, right, the noise, which is the black line, and then we turn off the pump, is there still that little peak when I turn off the pumping? The red, is there still a little peak? There is. That's because you still have spin projection noise. Those atoms are still adding noise. So we know even in this system, even though it's 10 centimeters cubed, we're still being limited by the atoms. So what do we want to do? This is just sort of a theoretical pushing. Well, let's add more of them, right? You know, if we're gonna let's go back to going big. So that's where somebody gave us money to do it anyway. They said, okay, fine, take her on up. We said, all right, fine, we'll take her on up. So this is a system that we're just sort of troubleshooting right now. Again, it's a collaboration with Michael Moss. And it's big. So remember, this is about a centimeter. And just to give you an idea, there's a pen. See the pen that's back there? Each of these spacings of these holes is 1 inch. So when you look to the thing to the right, it's big. It's not small at all. It's a very big system. Because it's big, there had to be some cleverness on how to get those passes. So in fact, this is what the light does in that system. It goes back and forth and back and forth again and again. Again, I'm allowed to boast because I didn't do it. It wasn't my design. I get to use it, but I think that it's an amazing design. Just to give you an idea of what things look like in the lab, whenever it comes back to the input mirror, this is this input mirror here, you can see these dots. Each of those dots represents 2 passes. You can actually look and see how many dots you have and how many passes you are, and count them up to know what you have. So you might wonder, why do I keep using 2 cells? Why 2 cells? I mean twice the volume, that's true. But another reason for doing that is you often want to get rid of common mode noise. Maybe you're looking for a signal, a small signal that's on one side versus the other side. So it'd be nice if we could use these 2 volumes and subtract noise from one from the other. So if you use light, we're talking about angular momentum. If you use angular momentum of light for one and use the opposite for the other, then the polarization of the atoms in the 2 boxes with their opposite directions. So again, you get subtraction. And I want to make it clear, when I talk about subtraction, people think about subtraction like signal processing. This is the light and the atoms are doing it. It comes out subtracted. So there's a lot of cleanness in having it not post-processed. So that's one of the reasons why we want to do this common mode noise, or these 2 boxes. The other one is actually what the people who gave us the money wanted us to do. We always kind of do things to decide we're interested in, but they're also interested in other things. And so it's also a nice idea. They asked us a question. They said, well, is it possible to encode upon one probe beam two signals, like 2 frequencies? Can you have like a 1 megahertz signal on one and a 0.5 megahertz on the other? Is it possible to have it be encoded upon one beam, those 2 signals? The answer is yes, as long as you have 2 different fields, magnetic fields. And so that's the idea behind that project. We've gotten some initial results, but haven't done it fully. So the initial results from this look promising. This is again this 46 passes a differential signal. And we've got the pump and the no pump, right? So again, the pump and the probe, and those are both on. That's that black line, no pump. We have a peak. And here, we come over here with the larger cells. Like again, remember 10 centimeter cube, or the magnitude bigger, right? So we upped it up a lot. So instead of being at 200 attatesla, so being 200 attatesla, we're below 100 attatesla. Again, I'm telling you, this is fresh, meaning it's not published. This is preliminary results. Don't hold me to it, right? So this is our initial results. And then I want to be really, really fair. Is that in fact that red line is when I don't have a pump beam on. So I'm really just checking to make sure that I'm not limited by spin projection noise. So Daniel here can keep me honest. If I put the pump beam on, what happens to my noise? If I get a much larger noise, maybe he doesn't remember.
Oh, yeah.
Yeah, so you get a much larger noise, and we know that we have work to do because we know our oven makes noise, and we know that we don't turn our light on slowly enough. So we've got work to do to actually make it when the pump beam is on at that level. So that's our current drive to see that. But we know at least that the atoms aren't going to limit us. So we have that assurance. And so we hope to do even better. Now it turns out, remember I talked about that 10 to the 14th centimeter cube. We're more like 10 to the 13th centimeter cube right now. And that's because with these glass cells, you remember the beam comes back and forth each time. And so you have to put anti-reflection coating on it. Otherwise, you lose too much light each time and you have no light coming out. So if I just use plain old glass, you get nothing coming out. There's actually 4% reflection for each surface. So you need the anti-reflection coating on it. The problem is that alkali atoms are really very, very reactive. Have you ever had any played with any alkali atoms? Probably nobody ever let you. But you know, I've created small fires with them by mistake and stuff like that. I mean, they're extremely reactive, and so they're also very reactive with the surface of this anti-reflection coating. So when we first use the cells, they often have very low number density because there's some impurities due to that coating. Over time, we have to saturate the impurities, and the number density goes up and up and up. So we believe that we can do actually an order of magnitude better in number density. We should bring this down by another factor of 3. So we think that this is very promising, but again, this isn't a sure result. Don't hold me to them. This is right where we are at the moment. So I hope that I've convinced you that at least optically pumped atoms can serve as great magnetometers. And just to try to hook up with what Joseph, is it Joseph or Joe? Joseph. Joe was trying to say. So when you do NV diamond centers, they really focus on small, right? Because they're little defects. So they're really, really great at having sensitivity for small volumes, for like surfaces and stuff like this. Really, the atomic magnetometers they're just at different beats. They're not small, but their sensitivity is better. However, if you want to measure something small, you're not going to use them either. So, but if you're going to measure something big, which sometimes you want to do, then this is kind of the way to go. I didn't really talk about applications. A lot of my funding is military, and what the military tend to care about is explosives. And so you can actually detect explosives using radio waves. You can put in radio waves, and you can see signals coming from the sample, from the explosive, and you can measure with a magnetometer. So that's where a lot of our funding has come from for this. I also hope to have convinced you that, well, maybe I haven't convinced you, but I hope I've convinced you to go talk to Jafar and Ratik at the poster session to find out more about how the quadrupolar nuclei can serve as the spy within to measure the fields. So with that, I want to, as usual, you give a talk like this, really a lot of people behind it. So there's 2 people, Jafar and Ratik, who I'm hoping you're going to talk to more. This is Cicely. She's at a conference right now. That's Daniel. If you're sitting right back there, you can bug him. He's done a lot of the work on the atomic magnetometer. Robert Cooper has also done a lot of the work. He's now at NRL doing optical clocks. My collaborator, Mike Morales, he's up there at the top. This is Nazif Dural. Nazif Dural did all of the glass work. He's like kind of like at the world's edge of people who do this kind of glass, heavy glass work. They also can be hot. So can you imagine it is this heavy? It goes up to 120 C. This is our 3rd version. The first 2 didn't work. So this is a picture of him. He's in my lab. He's got the mask on, working. And then there's Professor Mason here at GMU. He does the work with Jafar on the calculations behind those quadrupolar nuclei. So you might see him around campus. He's a good person to talk to. So on that topic of trying to find people, just like he said, I'm trying to find somebody. I need a postdoc, and quantum sensing is hot, and they're giving me money, and I need people. And so I'm a little frightened when he says that, because like, oh, can I get somebody? Because it's such a hot job market. And so that's certainly true. And if you're at that level, looking for a postdoc, please come talk to me or email me, and I'd be happy to talk to you about it. Any questions?
I don't know if this is a misguided question, but one of the applications is like potentially in medical, right? Like MRI machines or something, like replacing MRI machines.
So I did it last year, so I didn't do it this time. So MRI machines, they use coils. And so Faraday's law tells you that the EMF that's induced goes as the frequency of the oscillation, and the frequency goes as the field. So if you go to an MRI, over the years, the research centers, they keep getting bigger and bigger apparatuses to make me go higher, to make the mega go higher, to make the coil go higher. So when the frequency is high, the those coils go best. If you go down to low frequency, that omega, they stop working. So if you want to do an open MRI, then you need something like a magnetometer. That's the place for it.
Okay, yeah,
Because the sensitivity of the magnetometer is flat, and that coil is basically linear. 50 megahertz is the breaking point. Yeah, so that's for the low. That's every radio frequency of atomic magnetometers, which is. So let anybody know that. Do the same thing, you just apply a field to get the tuning.
I do have a question. How do you want it to talk? Curious to know how, if you have 40-foot passes, what happens? How do you know that one?
So actually, it's in the picture. I should have pointed it out, but I forgot to, as is usual when you give a talk. You feel like afterwards you said, oh, I should have said. So the entrance comes in here through a hole. Put a hole through the mirror. It comes in, it bounces back and forth, and then the mirror has, and then it comes, it just shears past that, goes through a lens, and it's hitting right here, that power meter. It just walks. It walks along that meter and then pops out over the edge.
How do you choose that number?
I don't.
Yeah.
This guy in Zero, who's like I said, really amazing. They do the calculations first and they do the simulation. They always tell you more than that sheet first, right? So it's, and when they give it to you, they tell you the number, and it is the number. You can count the spots, and you can go back and forth, and it's the right number. But when they're designing it, it's usually more passes than. And I really am not doing justice to what's. This looks simpler than it is, but really these mirrors behind you are curved. And so what it is, when you've got light that comes out from the fibers, you're probably aware that divergence. You have divergence, the mirror curves it, refocuses it on the mirror, goes out, refocuses it on the mirror again and again and again. So it's not even just the passes like I'm showing you. There's a constant refocusing, substantial refocusing. In fact, you want that in the atoms. You want the atoms to interact with light, otherwise ends not high. You gotta cover your cells. Any questions? All right, thank you for your attention.